So this is 7.4.4, capacitor charge and discharge. So in today's lesson, we're going to look at charging and discharging curves of capacitors, how that works, the equations behind it, and we're going to look at a quantity called the time constant. So let's set up a circuit that will allow us to charge and discharge a capacitor. So here we've got a cell on one side, and we'll label this plug here X and this plug here Y. We've got a capacitor in the center with a fly lead. Typically the fly lead could also be replaced by a switch that lets you switch between X and Y. So if we want to charge the capacitor, we take our fly lead and plug it into X. That will create a circuit between the cell and the capacitor. Charges will then be pushed onto the plates of the capacitor and it will charge it up. If we then want to discharge that capacitor, we can connect that lead to Y. That will create a current or cause a current to flow through the resistor on the Y junction, and you'll be able to read a current on that microammeter. So we charge at X, then discharge at Y. And we can record the current at suitable intervals.
If you connect it at X, how come the current will flow through that way? And why would it flow through Y?
What are you talking about?
You said that if you connect the fly lead to Y, there would be a current. If you connect it to X...
If we connect it to X, then the cell will charge the capacitor. If we connect it to Y, then the capacitor will discharge through the resistor.
You know the fly lead user? If we connect that to X and connect it to Y.
If the fly lead connects to X, it creates a circuit that has a cell and a capacitor, and it charges the capacitor. If I take the fly lead and I connect it to Y, then it creates a circuit that's got a charged capacitor and a resistor, and so current will flow out of the capacitor through the circuit, because a capacitor stores charge. And so once you've connected it across a resistor, that charge is now going to discharge. So it's going to flow. And if it flows, that's a current.
Yeah, when you connect it to Y, then the capacitor...
Well, if I replace the capacitor with a cell and I completed the fly lead to Y, you have no qualms with a current flowing. It's the same thing. If a capacitor has been charged, it's got a potential difference. If it's got a potential difference and you complete a circuit with it, well, V equals IR, so a current is going to flow.
But that's assuming that
the capacitor has been charged. We said that already.
Okay.
First we charge at X,
Yeah.
then we discharge at Y.
Okay.
The capacitor has been charged,
Okay.
so therefore it's going to discharge.
Okay.
Now, at the start, the capacitor has a large amount of charge, and because it has a large amount of charge at the beginning, therefore it has a larger potential difference. Because it has a larger potential difference, it's going to push the current more. So at the start there's going to be a large current, and as that capacitor discharges and there's less and less charge accumulated on the plates, the current through the circuit also reduces. So if we do an axis where we put time and current, we start at a large current and that decays as we go through time. The original current, we'll call it I0. Now because it's an exponential decay, it has something called a half-life, which is the time it takes for the current to drop by half its original value. So if we've got I0 over 2 here, that time that it takes there is called T1/2. And if we know if we know that that's the half-life, then if we go to I0 over 4, that will give us 2 times T1/2, and so on and so forth. Now I'm going to first give you an equation to work out the half-life, but later on we'll derive where this comes from. So, for the moment, T1/2 equals to CR ln 2. Put a box around that. So this is something you've learnt from GCSE, the half-life. But I'm going to introduce to you another quantity today called the time constant. So this is tau equals to RC. And tau is called the time constant, which is measured in seconds. And the time constant is defined as the time it takes for current or charge or potential difference to fall to 1 over E of its original value. And 1 over E is roughly 37%. Put a box around that definition. Right, next we're going to describe charging and discharging of capacitors using a water analogy. So let's imagine that the capacitor behaves exactly like a tank of water with an outlet at the bottom. If we discharge our capacitor, water will flow outwards. But if we charge the capacitor, we fill this tank from the same outlet. So charging moves water inwards. The height of the water, so how much water there is in that tank, gives us more water pressure. Yeah? So the height of water which is analogous to the charge gives rise to pressure, which is our potential difference. And a large pressure means that there will be a large current while discharging, but a small current while charging. And that's if pressure is big. So let's start from the beginning. We take a fresh capacitor. It's not been charged yet, it has zero charge on it. So in terms of the water analogy, this water tank is fully empty. In the beginning, when we're charging, it's very easy to fill water through that spout at the bottom or from the outlet because there is no water in the tank. As we start forcing water in and the water level starts building on the tank, that water exerts a pressure back. In other words, while we're trying to fill the water in the tank, the water is pushing back and trying to come out. So in the beginning, when we're filling the water, the pressure of water coming into the tank is large. The current of water, so how much water per second is filling the tank, is large in the beginning. But as the tank gets more and more full, the rate at which we're filling the tank slows down and down and down until we can no longer push any more water in, because the pressure at which we're pushing the water in becomes the same pressure as the water that's trying to push back out. And that's the same as a capacitor. The potential difference we're using to push charges onto the capacitor becomes the same as the potential difference of the capacitor pushing back. And that's why when you've charged a capacitor, it reaches the same potential difference as the battery or cell that you're using, and then current stops flowing and the capacitor stops charging. If we then begin the discharge process, in the beginning there's a lot of water, which means there's a lot of charge stored. If there's a lot of charge stored, there's a lot of pressure, which means a lot of potential difference. So in the beginning, all that pressure is going to push the water out very, very quickly, so there's going to be a large current. As that tank empties, the pressure will lower, which means the voltage will lower, so the rate at which the water comes out of that tank begins to slow down, which basically means that the current begins to reduce. Once that tank is pretty much empty, all you get is a small amount of drops coming out. So at that point, your current is almost zero. Your current goes very, very low. Now, those descriptions can be graphed. So you might need to, at some point, go back and listen to the explanations and the wording, and then imagine how that would look like on a graph. So our graphs, we'll do charge at the top, and we'll do discharge at the bottom. So on the x-axis, we'll do charge. Sorry, on the y-axis we'll do charge, and on the x-axis we'll do time. When empty, it's easy to charge, so charge builds up very quickly in the beginning. But the rate at which charge builds up slows down as we get to it becoming full. So in the beginning we have no charge. At the end we're full. But the rate at which, so the gradient of the graph, the rate at which charge is pushed onto the capacitor or into the tank is large at the beginning, but slows down at the end.
The gradient of the graph is a current.
The gradient is current. Now we can do current. Current is large at the beginning, but current slows down as we get more and more full. And you can compare the gradient as well. The gradient is very large at the beginning, but then becomes zero right at the end. So current is an exponential decay. Now the potential difference or the pressure is zero at the beginning when it's uncharged, when the tank is empty. As we fill it in, because we're increasing the amount of charge very rapidly, our potential difference or our pressure in the tank builds up very quickly, but then it levels off, just like the charge. So it also looks like this. Now for our discharge graphs, in the beginning we have a full tank. We have maximum charge. At the end we have no charge, or very little charge. And the rate at which charges flow, it flows faster when it's full outwards, which means current is large in the beginning. And the amount of charge, the rate at which it decreases, will slow down at the end, so it will level off. So this gives us an exponential decay. Our current, if we look at the gradient, is large at the beginning and small at the end. So our current is also exponential. Now you might be thinking, but it's negative. The gradient is negative. Yes, it is, but we're only looking at the magnitude. And the potential difference, again, if it's full, there's a lot of pressure. As it empties, its pressure declines. Its pressure decreases more rapidly at the beginning when water's gushing out, and when water's just dripping out at the end, the rate at which the pressure drops, or the potential difference drops, is also less. So that's also an exponential decay. In other words, for the discharge, all three graphs look exactly the same. Now I'm going to give you the equations for discharge because they're easier. And then I'll give you the charge equations after that. For now, just learn the equations, but later on we're going to explain why they are the way they are. So our discharge equations, these are the easiest ones to remember. So Q equals to Q naught e to the power of minus T over RC. Then we've got I equals to I naught e to the minus T over RC. And then we know that V is equal to IR. And if we've got V naught is equal to I naught times R. So if we were to multiply all of this by R, we get IR equals to I naught R e to the minus T over RC. And that will give us V equals to V naught e to the minus T over RC. So all three equations are the same for discharge. And that makes sense because all three graphs were the same. So this Q and that I and that V, all are basically the same. So Q is how much charge is on the capacitor at given time. Q naught is the charge on the capacitor at the start only. So charge on capacitor at given time. So Q changes. And Q naught is the initial charge. The charge at t equals 0. So likewise here, I naught is the current at t equals 0. I is the current at given time t. V naught is the potential difference at t equals 0. And V is the potential difference at given time t. Now, in terms of the experimentation, we cannot measure Q directly. So we don't know what charge is on the capacitor at given time t, because it's changing constantly. So we can use an ammeter, that will give us current. We can use a voltmeter, that will give us potential difference. But we can't measure the charge that's actually on the capacitor. Now I'll give you the discharge equations. The charge equations, we've done the discharge. So for charge, we got Q equals to Q naught, 1 minus e to the minus t over RC. For current, it looks the same as it did before. I equals to I naught e to the minus t over RC. That looks like a E, RC. And for potential difference, it looks just like the charge. So V equals to V naught 1 minus e to the minus t over RC. And for current, there's going to be another version of this, which is I equals to Q naught over RC e to the minus t over RC. And that's the end of part 1 of 7.4.4.